Tonight, as the room hushes and the moon paints a thin silver path along the wall, let's curl up with a soft story about the smallest things. Quantum physics, explained slowly, like a lullaby for curious minds, doesn't arrive with thunder. It comes as a whisper, a ripple in a quiet pond, a shy glint at the edge of a thought. We won't rush. We'll breathe together, letting each idea float past like lanterns on a midnight river, particles that are sometimes waves, choices that flicker before they're made, a universe learning itself in tiny, tender steps. If your eyelids grow heavy, that's all right. Understanding can be a feeling before it becomes a fact. Imagine the air around you as a gentle sea. With every inhale, you rise, and with every exhale, you drift. In this calm, the abstract softens into shapes you can almost touch, a grain of light, a hush of probability, the quiet heartbeat of an atom. And if this warm corner of night feels like home, a light tap on like and subscribe helps keep the lamps low and the stories glowing. No hurry, no fuss. When you're ready, we'll step together into the small and listen for what it has to say. What is quantum physics, really? Why does it sometimes feel as if the cosmos is improvising, composing each moment as softly as breath? The everyday world seems sturdy and sure. A cup slips and shatters. A coin arcs, spins, and settles. The moon keeps its patient vigil whether or not your eyes are open. Yet, when the 20th century was young and the lights of modern science grew brighter, curious minds leaned closer, closer than anyone had dared to the hidden seams of matter. The nearer they drew, the odder the stitching looked. Light, long treated as a rippling wave, also arrived as tiny pulses, as if the sea could be counted by drops. And those drops, the particles of the world, refused to stand in a single place until someone looked for them. Observation did not merely uncover what already was, it seemed to coax reality into choosing, as if measurement were a fingertip skimming a still pond, sending patterns outward. This was no smear of faulty instruments. It repeated again and again under careful hands. Classical laws, neat as polished floorboards, began to creak. Quantum physics was not just a fresh chapter, it was a lantern turned at a new angle, revealing a room where certainty thinned into likelihoods and where cause sometimes wandered a step behind effect. Tonight, we will float through that room without hurrying. Equations may rest for later. Names can drift like distant buoys. We will take small, quiet steps from the first puzzles that jostled scientists from their comfortable stools to the open questions that still whisper to them long after midnight. Settle your body. Let the mind loosen. We are headed toward a place where emptiness isn't truly empty, where truth arrives with a probably, and where the familiar agrees to blur at its edges. At the turn of the 1900s, physics felt almost sewn up. Motion bowed to rules. Heat behaved with tidy logic. Light fit snugly within Maxwell's grand weave of electromagnetism. It was an age that loved closure. Some even declared that the big mysteries had been cleared away, leaving only a few crumbs to brush from the table. One crumb, ordinary as it seemed, glittered oddly under the lamp. What does a warm thing do? Heat a poker or a coal, and it glows first red, then deeper, then a pale white as the temperature climbs. This glow, called black body radiation, is the light poured out by matter when it is heated. Easy to see, simple to describe, it looked like a problem tailor-made for the old equations. But the numbers would not yield. Classical physics predicted a wild surge. According to those formulas, as temperature rose, an ideal blackbody should flood the world with energy at higher and higher frequencies. especially in the ultraviolet. Follow the math to its edge, and the energy becomes infinite, a fantasy so absurd it earned a wry name: the ultraviolet catastrophe. No clever sanding of the equations could smooth that cliff. The universe was refusing the story the calculations told. Something essential had been left out. Enter Max Planck, around 1899. The quiet German theorist, careful and conservative, approached the puzzle. Planck did not relish revolutions. He trusted the classical picture, yet he was stubborn about truth. Facing the black-body snarl, he tried a modest, peculiar move. Suppose energy could not be paid out in any amount at all. Suppose it came in tiny coins that could not be split, each coin sized by the light's frequency. He named these coins quanta. This traded the continuous stream of energy for a staircase of little steps, no sliding, only jumps. Planck introduced a constant to set the size of each step, a number so small it felt like a whisper tucked inside nature. Slip this idea into the equations, and a surprising calm arrived. The infinity evaporated. The curve matched the laboratory lamps and furnaces. The catastrophe dissolved like fog in morning sun. Planck, however, did not lift a flag and sing. He treated his fix as a mathematical convenience, a way to make a stubborn curve behave, not a window into what the world truly is. Surely, he thought, a more comfortable explanation would come later, one that kept energy smooth and continuous. To him, quantization was a patch sewn across a torn seam. He could not guess that the patch would become the fabric. That small step, the notion that energy is delivered in discrete packets, laid the first stones of a path soon, called quantum theory. Along that path, the assumptions of classical physics would loosen, thread by thread. From our vantage, it is tempting to circle the date and call it the dawn. In its own hour, it felt more like a margin note than an uprising. Planck had not set out to overturn a worldview. He wanted an answer that fit the evidence. Yet by daring to imagine energy in pieces, he struck the match for a long, careful fire. It would take years for the glow to spread, to reach discussions of electrons and atoms, to touch the way we think about measurement, to ask whether reality waits for us or moves on in a blur of maybes. That first paper, published quietly in 1900, did not roar. It offered a constant, a new rhythm to energy, and a tidy solution to a problem that had embarrassed the best minds. From then on, physics no longer felt neatly finished. The edges remained soft, the floorboards alive underfoot, and in that living floor, under the hush of night, a new kind of story began, one told in gentle quanta, in probabilities that breathe, and in a light that sometimes arrives as a wave and sometimes as a countable drop. We'll keep listening, moving slowly. We drift a little farther into the quiet, where the air softens and thoughts loosen their knots. For a long stretch, many believed light had settled a graceful wave running through an electromagnetic ocean, ripples crossing with predictable grace. Maxwell's equations made that ocean hum, showing how beams bend, reflect, and diffract with the steady rhythm of a tide. After Planck suggested that energy might arrive in tiny steps, most expected a modest correction to the chart, not a new course drawn after dark. On a simple bench, a metal plate waited beneath a lamp. When light rested on that surface, small sparks electrons sometimes leapt away. The story sounded straightforward. Light delivers energy, energy loosens bonds, electrons escape. But as experimenters turned knobs and tuned colors, the metal answered in a different tongue. Brighter light did not always give electrons more speed. Raising intensity could leave the surface unchanged. Shift the color toward higher frequency, though, and electrons would suddenly fly free. A boundary stood there, sharp as a cliff at low tide. Below a particular frequency, no amount of brightness worked. Above it, even a soft glow could free electrons with calm certainty. The classical story struggled. If energy is smeared across a wave, then simply adding more wave should eventually push some electron over the edge. Yet the metal cared less about volume and more about pitch, like a door that opens only when a certain note is sung and stays shut to any louder, wrong tune. The riddle looked modest, yet it opened like a hidden door. In 1905, during a year lit from many angles, Albert Einstein picked up Planck's thread and tugged. Imagine, he suggested, that light can arrive not only as a spread-out wave, but also as separate parcels, droplets that keep their identity as they travel. The energy of each droplet is fixed by its frequency, higher frequency, richer parcel. He called these parcels light quanta. Later we would give them a gentler name, photons. With that single turn, the benchtop behavior settled into sense. Every photon carries a fixed budget of energy. If that budget meets or exceeds the metal's price, the work required to pry an electron free, the electron departs. If the budget falls short, no crowd of photons can help. It is like standing at a locked door with a pocket full of almost right keys. More keys do not help if none of them fit. The sharp threshold follows from this picture, and the measured energies of the ejected electrons march neatly with the light's frequency. Einstein did not discard the wave to make room for the photon. He widened the frame so both pictures could stand. Ask one kind of question, and light spreads, interferes, and diffracts like a wave. Ask another, and it arrives as a countable visitor, one packet at a time. We call this wave-particle duality, but in a late-night room, the idea feels simpler. Picture a sunbeam through dust, a veil drifting across the floor. Lean closer, and you can almost hear gentle footfalls, photons, tapping what they touch. Many physicists hesitated. The wave model had explained so much, and with such elegance, that letting particles into the room felt like rearranging the furniture of reason. But the experiments were steady, and the mathematics drew clean lines through the data. In 1921, the Nobel Committee honored Einstein's explanation of the photoelectric effect. Relativity may have captured imaginations, yet it was this spare, careful account lamp, metal, electrons, that earned the prize and quietly reset the conversation. Even then, Einstein stood somewhat apart from the deeper currents that followed. As quantum theory unfolded, it suggested that probability is stitched into measurement, that outcomes bloom from chances rather than hidden certainties. He bristled at that prospect. God does not play dice with the universe, he said, preferring an order veiled rather than absent. The debate never truly drowsed, but whatever anyone believed about dice, the photoelectric effect remained a lantern that refused to dim. What does that lantern show? That light is layered. Intensity tells us how many photons arrive each moment. Frequency tells us how much energy each one brings. A bright, low-frequency beam may flood a room and still fail to free a single electron. A faint, high-frequency beam can send electrons stepping away with quiet confidence. The metal does not negotiate. It waits for a key cut to the right shape and admits nothing less. Let that picture settle. A quiet bench, a clean plate, a lamp gliding through color. For a while, nothing changes. Then, at a particular hue, there is a peppering of departures, small, sudden, certain. In that instant, the quantum story stops feeling abstract and becomes tactile, like a pulse you can sense at the wrist. The universe keeps its wave music, yet it also counts in single steps, 1, 2, 3, in the soft space between breaths. We can rest with that rhythm. This is how the quantum world likes to speak, in thresholds rather than ultimatums, in invitations rather than commands. Light, our oldest companion, refuses a costume. It can be mist and it can be beads, veil and footfall, chorus and rain. And as the night draws deeper, the lesson becomes a lullaby. Listen closely, and the next idea will arrive like a soft knock at the door, carrying just enough energy to open what waits on the other side. Picture a darkened room, the kind that softens your breath and makes sounds seem farther away. On a modest table sits a lamp, a sheet of card with 2 slender windows, and a quiet screen that waits like snow for first footprints. Within this small theater, 2 slits and a little light, the world reveals one of its most intimate secrets, the kind that appears only when we ask with patience. If a lake sends ripples through a pair of gaps in a pier, the waves spread, overlap, and lace the surface with bright crests and shaded hollows. That is interference, a choreography of arrival and cancellation. If you swap waves for pellets, little rubber balls tossed at a wall with 2 openings, you do not get lace. You get 2 neat mounds where the balls thread the holes and thud to rest. Waves weave, particles pepper. We shine light through the 2 slits and watch the screen bloom with alternating bands, bright, dim, bright, dim. So far, all is wave. Maxwell's field ripples, and the slits play it like a quiet instrument. But then, as the lamp is hushed to a whisper, we begin sending single quanta photons one by one. Each is a tiny visitor, a soft footstep. Common sense leans in and says, the photon must choose, left slit or right slit, not both, not neither. Give it time, let the dots collect, and surely 2 bright humps will rise behind the slits. The screen disagrees. The points gather slowly, like snowflakes settling, and an interference pattern emerges again, those same bright and dim bands, born not from a teeming stream, but from solitary travelers accumulating over minutes and hours. It is as though each photon spreads into a possibility cloud, slips through both openings at once, and then writes a single dot where all its maybes agree to meet. A single wave and a single impact, sharing one quiet arrival. It feels like a confession from nature. Curiosity cannot leave it there. We place small watchers at the slits, devices ready to whisper, left or right, nothing more. We promise not to shove, not to disturb, only to know. And the moment we invite knowledge to sit beside us, the pattern changes. The soft lace of interference fades. The dots collect in 2 humbler piles, left and right, like pellets, after all. We stop asking which, and the lace returns. We ask again, and it vanishes. The room seems to exhale, as if the act of noticing had pressed the world into choosing. This is not the clumsiness of probes jostling delicate things. The arrangements can be gentle, the watchers light as moonbeams. What matters is not the push, but the possibility of an answer. The potential to know the path is enough to fold the spread-out wave of chances into a single, definite mark. In that folding, a word takes root: measurement. It does not merely read, it participates. It helps decide which of the many glimmers will solidify into now. The experiment is not precious to photons alone. Electrons trace the same shy pattern. Even molecules, bundles of atoms large enough to feel almost homely, can sketch interference when we let them wander unobserved, and will line up like punctual beads when we insist on paths. Left to itself, the microscopic world behaves like a mist of possibilities, dispersing through both doors at once. Asked to account for itself, it walks through one door with calm finality. How do we speak about this without waking the room with argument? Some tell the story as a wave that splits and later reunites, a self that travels along twin threads and then gathers itself whole. Others prefer a quieter language. The wave is not stuff. It is a map of likelihoods, a guidebook we use to predict where a dot might appear. The map collapses when we open it to a specific page. And there are those who imagine a broader hush. Perhaps every possibility is realized, each in its own quiet branch. Whatever story we choose to tuck around the data, the shared heartbeat remains. Before we look, the outcomes are spread like stars, in fog, distributed, tentative, humming with maybe. When we look, the fog condenses into a single star, and the rest fade from our sky. The universe, at this scale, does not march like a clock. It drifts like breath, and our noticing sets the cadence. You can feel the softness of the lesson in your own body. Inhale, and many futures expand. Exhale, and one arrives. The screen does not lie. Two slits can make a fabric from light, or from matter itself. A fabric that tears the instant we tug for certainty. And so, a humble table becomes a mirror for a deeper question. Is observation simply watching, or is it a kind of touch, a fingertip on the still pond that raises a ring and says, "Here"? The answer is not a pronouncement, but a practice. We test, confirm, repeat. The bands appear, vanish, reappear, as reliable as tides under a patient moon. From these tides, we learn that the smallest things travel as possibility and arrive as a point. That knowledge fashions the point's address. That information, mere capacity to be known, has weight enough to bend the story. It is unsettling only if we demand the world be rigid. If instead we allow it to be supple, the lesson becomes almost restful. Imagine returning to the room after midnight. The lamp is low, dust hangs like tiny planets. You open and close the watchers and watch the pattern answer, yes, no, yes. You are not bullying reality. You are conversing with it in questions and nods. The slits are a doorway into that conversation, an invitation to feel how the universe listens as much as it speaks. And perhaps the kindest way to hold the result is this. At the smallest scale, being is a shimmer of choices, and seeing is the moment one choice becomes home. The screen records that settling, dot by dot, like a lullaby written in light. We do not need to solve the mystery to rest with it. We only need to notice that in the gentle game between veil and glance, the world is both wave and particle, both drift and landing, and that our attention, offered softly, helps decide which face it shows. In the hush between heartbeats, imagine a single line of mathematics, humming like a lullaby, not to jolt you awake, but to move things along beneath the surface. In the 1,920 seconds, when old mechanics felt a size too small, Erwin Schrödinger offered a gentler language for particles that behaved like ripples rather than marbles. His 1,926 equation doesn't shove objects. It listens to how a quantum system breathes, then tells how that breath changes with time. Symbols may look thorny, but the story is tender. Here is how possibility flows. At the center sits the wave function, psi, an invisible fabric draped over space, mapping where a particle is likely to greet us if asked. Classical physics draws a sharp arrow. Schrödinger sketches a tide, higher here, lower there. His equation governs that tide, smooth, continuous, honoring deep symmetries. Left alone, psi unfurls reversibly, like a melody. Ask, "Where are you?" And the fabric narrows to a point, a single answer. Before the question, many doors stand ajar. After, one closes with a soft click. If collapse sounds mystical, think of ringing a bell in a dark hallway and mapping the room by echoes. That imagined map isn't the hallway itself. It's a guide to what you'll find when you look. So too with psi, an atlas of likelihood, and Schrödinger's equation, the rule for how the echoes shift as you move. Build atoms from this softness, and electrons aren't tiny planets. They gather as standing waves orbitals, like clouds and petals, regions where an electron is likely to dwell. Hydrogen sings in discrete notes because only certain standing waves fit. Each carries a specific energy, leaving crisp lines in spectra and starlight. The old worry, why don't electrons spiral into the nucleus? Dissolves. What orbits is a wave, and waves choose patterns that endure. From this seed, a forest grew. The same equation explains chemical bonds, the shared presence that glues atoms, the band structure of semiconductors guiding currents in your phone, superconductors where paired electrons move in a collective hush, and tunneling, where a wave seeps through a barrier and appears beyond, like a quiet thought slipping past doubt. What psi means remains open. Is it a book of our knowledge, updated by measurement, or real furniture of the world? Interpretations bloom, Copenhagen's pragmatic shrug, pilot waves shepherding hidden paths, many worlds unfolding every option in parallel rooms. Schrödinger's equation takes no sides. It simply evolves psi, whether we call it map or meadow. Even Schrödinger felt the strangeness. He cherished the equation's elegance, but distrusted the idea that things are definite only when looked at. Hence the cat, a macroscopic fate knotted to a quantum event, alive and not yet alive in one description until a record is made, a protest that also reveals what the math allows. Superpositions and entanglements that persist. You can't ladle psi with a spoon, yet its fingerprints are everywhere. Spectral lines, crystal energies, tunneling rates. Experiment asks politely, and the numbers answer with grace. No patches, no exceptions, just a steady fidelity to the tiny. To sit with this is to accept a softer rule book. Motion, not always a path, but a swelling and thinning. Position, not a dot, but a hush across a room. Certainty, not default, but a gift after we decide what to ask. Schrödinger did not hand us a spotlight to burn the fog away, but a lamp to read its patterns, the way it curls around corners, the way it clears as we choose a direction. And so the equation continues, quiet and exact, evolving possibilities while the world sleeps. It doesn't settle every quarrel about what is truly real. It keeps time and delivers results we can hold, from circuits to distant spectra. In a universe that begs for yes or no, here or there, this one line of mathematics offers a gentler reply, maybe here, maybe there. Until asked then, a single answer, and afterward the fabric drifts again, rippling softly through the dark. In the daylight world of stones and coffee cups, certainty feels ordinary. A car's place and speed fit in the same breath. bend down to electrons, and knowing becomes a trade. Clarity gained on one shore is lost on another. In the 1920 seconds, Werner Heisenberg gave that trade its name, the uncertainty principle. It isn't clumsy measurement, it's how nature is. Pin position precisely and momentum wriggles free. Sharpen momentum and position blurs. Disturbance by light is a real effect, but the deeper reason is wave nature. An electron's state is a wave function possibility rippling through space. Squeeze a wave into a tiny region, and it must carry many momenta, like a sharp pluck that blooms with many notes. Let it spread smoothly, and its momentum narrows while whereabouts spill out. No loopholes. Mathematically, the product of uncertainties in position and momentum can never drop below a hard floor, Planck's constant over 4 pi. That constant is tiny, so at human scales, the limit hides beneath everyday noise. Inside atoms, it is bedrock. Try to pen a particle into a nook, and its momentum, uncertainty, and kinetic agitation swells. Squeeze harder, and the energy cost soars. Electrons, therefore, do not fall into the nucleus. They hover in standing wave orbitals, soft patterns that endure. Think of cupping mist. The tighter you close, the more it slips away. Loosen a little, and more lingers. So here, precision on one side, forces release on the other. This isn't chaos, but structured softness. It enables tunneling waves, seeping under barriers, and zero-point motion, the whisper of movement that survives even at the coldest temperatures. The reach is wider than position and momentum. Energy and time share a similar give and take. Razor-sharp energy demands a longer window. An exact, fleeting moment forces energy to blur. Angular momentum and orientation trade certainty the same way. Everywhere in the quantum room, knowledge arrives in coupled steps. None of this declares the world unknowable. It says knowing has a coastline, scalloped rather than straight. We can chart it exquisitely. At small scales, the answers are probabilities, and the questions we ask help shape which answers can arrive. Paradoxically, the blur is what lets matter stand. Without it, atoms would collapse, spectra would smear, and chemistry's lattice would fail. With it, discrete energies and springy bonds appear. The small stays whole. So don't picture a bead racing a track. See a hush spread through a room, thicker here, thinner there, always in motion even when bound. Point too sharply and the hush recoils. Grant a little grace, and it rests in faithful shapes. Philosophically, is the limit on what we can know or on what there is to know? In practice, the difference softens. The universe keeps its promise. Outcomes come with spreads, and the spreads themselves mean something. Heisenberg didn't give darkness. He gave a lamp with a dimmer, a way to move without kicking the furniture. We still navigate and predict, building microscopes, lasers, sensors, and chips that honor the shoreline. The certainty we surrender is repaid with patterns that hold. Listen closely, and the principle has a lullaby. Peace with a gentle blur. Truths spoken as ranges rather than points. Beauty that endures without hard edges. In the daylight rules, things commit. A coin shows a face. A lamp is on or off. Far below, the small does something gentler. It lingers as both. That is quantum superposition, a state where multiple possibilities breathe at once. The wave function is the soft script beneath this, holding options as amplitudes, like notes in a chord. Before we listen, the chord is the truer thing. A measurement resolves it to a single pitch. Schrödinger's cat sharpened the feeling. Tie a tiny quantum event to a macroscopic fate, and, before a record exists, the story reads, alive and not yet alive. Absurd at scale, yet faithful to the mathematics that keeps winning in the small. Superposition isn't a bug, it's power. Qubits can rest in 0 and 1, letting interference weigh many answers at once, useful for simulating molecules and navigating huge optimizations. The same softness safeguards communication. Quantum key distribution leaves tampering fingerprints and heightens sensing, teasing out faint magnetic or gravitational shifts. This is no sci-fi promise. It's today's lab work, but the state is tender. The world's bumps and whispers, warmth, vibration, stray light nudge superpositions to declare too soon. That unintentional measurement is decoherence. Keeping the both alive means cooling, shielding, isolating, and error-correcting cradling qubits as velvet cradles glass. Fragility isn't failure, it's the price of specificity. What is psi? A ledger of knowledge, or a real field the world wears? Interpretations differ. The math is agnostic, advancing psi and yielding numbers that match the world with uncanny grace. Perhaps let it be a posture, not a paradox. Superposition says opposites can share a breath without quarreling patterned ambiguity that lets electrons find homes, molecules bind, and computation discover new paths. Think of a softened coin tossed in the dark until you ask. It genuinely holds both faces. Your question chooses a faithful note. In silence, the chord returns. That may be superposition's gentlest gift, loosening the grip that insists every story has one thread from the start. The universe, it seems, braids letting several futures travel together until the moment calls for one, a room of soft doors waiting for the question that chooses which we step through tonight. Before sleep takes the room, hold the glove picture lightly. Classically, each box already carries left or right. In the quantum hush, though, each glove is a braid of both until you look. Open one box and the other, however far away, settles in the complementary way. That instant, perfectly matched settling, is entanglement, a single wave function stretched across two things, so that a question asked of one thread draws a pattern through the whole cloth. No signal sprints between them. Each outcome is random by itself, yet the pair is choreographed together. Einstein, uneasy with such non-local ties, hoped hidden variables might restore local cause and effect. Bell later drew a clean test, and experiments tight, loophole-free, kept returning the same answer. Nature violates Bell's inequalities. The world is not governed by any local script of pre-written results. The correlations are too exact to be private plans. Still, entanglement is kind to causality. It can't send messages faster than light. You can't choose your result to wink across the cosmos. Only when notes are compared do the correlations bloom. Distance doesn't dilute the bond photons sent across cities, and by satellite, stay in step because the link lives in the shared state, not in space between. What is this tie, then? Some say it is structure in what we can claim about the joint system. Others accept a deeper non-local bookkeeping where space isn't the final ledger. Bolder whispers suggest space-time itself may be woven from such patterns that geometry is an echo of countless microscopic ties. Either way, the lesson is soft and sure. Separated things can still belong to one sentence, and when you ask one word to speak, the meaning settles everywhere at once. Entanglement isn't dream work, it's hardware. It powers quantum teleportation, moving a state, not stuff. Anchors quantum key distribution, where any eavesdropper leaves indelible smudges, and fuels quantum computing operations, woven across many qubits, in harmonies no classical circuit can mimic. It never sends messages faster than light. Each side sees only randomness until records are compared. But the shared state is delicate. Stray warmth, vibrations, or light can fray it into ordinary threads. So engineers cool and shield, encode and correct hands, cupped around candles, keeping the chorus coherent just long enough to be useful. Relativity and quantum theory keep a workable truce. Correlations may be instant. Communication is not. And then, the lantern cat. Schrödinger's fable was never a blueprint, but a mirror for our intuitions. Tie a truly random atomic decay to a macroscopic fate, and, before a record exists, the description stretches alive, and not yet alive. The puzzle is measurement. Between questions, the wave function flows deterministic, reversible, like music that can run forward or back. When information is drawn out, the spread narrows to one line. What counts as drawing out? Copenhagen says, treat the wave function as a tool. Speak only of registered outcomes. Many worlds keeps the flow unbroken and lets each outcome live in its own branch. Decoherence shows how superpositions leak phase into the environment until interference is lost, and the scene looks classical, not because possibilities are destroyed, but because they're inaccessible. Beneath the debate, one truth sits steady. Quantum systems are not tiny billiard balls. They evolve as delicate waves of possibility, and which facts arrive depends on what can, in principle, be known. Scale changes our intuition, not the rule. Lay down which way information and fog thins to a track, keep possibilities intertwined, and the chorus still sings. Entanglement isn't dream work, it's hardware. It moves states, quantum teleportation, hides keys in fragile correlations, QKD, where eavesdropping leaves smudges, and lets quantum computers weave operations no classical circuit can easily mimic. It never carries messages faster than light. Each side sees randomness until notes are compared, but it is delicate. Warmth, vibration, stray light, fray the shared state. So we cool and shield, encode and correct hands cupped around candles, keeping coherence just long enough to use. Relativity and quantum promise a truce. Correlations may be instant, communication is not. Beneath it all is a quiet comfort. At small scales, separateness is sometimes an illusion. Distant parts can still belong to one sentence. The lantern cat remains a mirror, not a blueprint. It lights the measurement problem without pretending to solve it. Between questions, the wave function flows, reversible as music. When information is drawn out, possibilities narrow to one line. What counts as drawing out? Copenhagen treats psi as a predictive tool. Many worlds keeps the flow and lets outcomes live in disjoint branches. Decoherence shows how phase leaks to the environment until interference is lost and the scene looks classical. Steadier than the debate is the lesson. Quantum systems aren't tiny billiard balls. They are delicate waves of possibility, and which facts arrive depends on what can, in principle, be known. Tunneling softens our faith in edges. A particle's wave doesn't halt at a wall. It tapers through, leaving a small chance to appear beyond no magic, just amplitudes that seep. That sliver explains alpha decay's escapes and lets stellar cores fuse despite fierce repulsion. We harness it on Earth. STMs read atomic landscapes from tunneling current. Tunnel diodes and quantum dots exploit it in devices. Ever thinner transistors must tame unintended leakage. Josephson junctions use coherent tunneling to sense exquisitely and to host qubits. The philosophy is gentle. Boundaries are slopes, not cliffs. A barrier doesn't forbid it ways. One trial looks like whimsy. Many trials sketch a law. And if you tilt your ear toward nothing, even emptiness won't sit still. The quantum vacuum hums under the silence, a restless stage where possibility never quite goes to sleep. Here's a gentler, tighter weave of your two passages, same ideas, softer footprint. Why should nothing have a pulse? Start with uncertainty. Heisenberg ties energy to time, allowing brief, rule-abiding flickers in the vacuum, virtual pairs that rise and vanish, leaving only the marks they press into what we can measure. One mark is the Casimir effect. Two plates set nanometers apart feel a tiny squeeze because the narrow gap edits which vacuum ripples fit between them. The vacuum also leans on atoms and particles. QED's virtual photons mediate electric pulls. The proton's heft comes largely from a sea of quarks and gluons. Even hydrogen's levels shift by a whisper, the Lamb shift. Cosmology wonders if vacuum energy helps drive cosmic acceleration, even as naive sums overshoot reality by an absurd 10/120 a map pin that reads, "Mystery here." So emptiness isn't absence. It's potential, the quiet baseline every field plays against. Then comes the most human turn. What becomes of a quantum thing when we finally look? Before the question, a wave function carries possibilities. Position as haze, spin as chord, motion as many routes at once. A detector asks, which? And the mist narrows to a single answer. We call it collapse. What stirs that click remains uncertain. Apparatus, information flow, the warm, watchful environment. The math is kind. The meaning stays just out of reach. Traditions sit in different chairs. Copenhagen treats the wave function as a book of odds and speaks only of registered outcomes. Many worlds refuses the snap, letting every outcome live on in separate, non-communicating branches. Objective collapse models make reduction a real, spontaneous physical event that grows likelier as systems grow. Cubism says collapse is an update of an agent's beliefs. Threaded through all is decoherence. Stray photons and vibrations entangle a system with its surroundings, bleeding away the phases that would let alternatives interfere. The scene looks classical not because other possibilities are destroyed, but because they've been woven into correlations we can't recover. Across these views, a handful of truths hold. The calculations work with breathtaking precision. The dot we see is drawn from the fog's shape, and the line between smooth evolution and recorded fact is still an open book. Perhaps new physics waits there. Perhaps the working rules are enough. Stand, then, under a wide, dark sky. Even where no starlight falls, the vacuum hums. Instruments feel its nudge. Spectra carry its signature. And inside the lab and our lives, certainty arrives under conditions. When and how, we ask. It needn't feel like a flaw. The universe keeps possibilities open, then exhales one into being when touched. In that hush between maybe and must, let the mathematics lead, let language tread lightly, and rest in a world that is softer, stranger, and more generous than nothing or now first suggest. If a metaphor helps, imagine water cooling toward ice. At some point, the texture changes, and liquid certainty gives way to crystalline fact. But unlike water, we do not know the pressure or temperature that govern the change. We only know that when a record is made, when a mark is etched that cannot be unetched, the superposition's sheen goes dull, and one facet remains in your hand. Perhaps collapse is our word for that making of records, the knitting of a result into the world so tightly that it cannot be undone. Or perhaps the kindest truth is simpler and stranger. Perhaps nothing in the world collapses at all. Perhaps what falls away is only our insistence that a thing must always be one thing before we ask. The universe may be content to hold multiple futures near its chest, to carry them like a chord sustained, and to offer a single note only when the music calls for it. We are the ones who long for a single line. What then happens when we measure? It could be contact with a device. It could be entanglement with a room that never forgets. It could be our own beliefs brought current. It could be branches parting like quiet rivers. It could be a piece of physics not yet written, folded between quantum law and space-time's curves. We can keep breathing with the question. We can keep building instruments that hold superpositions tenderly and then let them go. We can keep listening for the place where fog becomes shape. And we can allow, in the dim before sleep, that the answer may be stranger than we hoped and truer than we imagined. A world that loves possibilities, that consents to presence when asked, and that leaves, in the space between, a patience we can feel if we grow very still. If quantum physics kept an address, many would jot down Copenhagen not for the windmills or the bicycles gliding over cobblestones, but for the quiet rooms where late-night arguments softened into a new way of seeing. At the center sits Niels Bohr, gentle voice, careful words that looped like canals, and a stubborn sense that the world at small scales asks us to speak differently. From those rooms emerged the outlook we now call the Copenhagen interpretation. Its charm is in its plainness. A quantum system, it says, does not carry fixed properties the way a pebble carries weight. An electron has no settled position. A photon does not pledge a polarization. Before we ask, the system is a drifting cloud of possibilities, a wave of probability. The act of measurement does not peel back a curtain to reveal what was already there. It is the moment the picture comes into focus. The outcome is created in the asking. That sounds like a riddle designed to keep philosophers awake and send physicists for stronger coffee. But Bohr and his companions weren't courting mystery. They were obeying experiments. Treat quanta like tiny billiard balls, and the equations tangle. Treat them as probability waves that condense into facts only when we measure, and the numbers fall gently into place. In this view, the wave function is not a little fog coiled inside the particle. It is a ledger of what can be said, a catalog of chances, not a map of what is. Questions about the system's state before measurement lose their footing. Where was the electron? Has no purchase, because where becomes a meaningful word only after the device writes a mark. Reality does not sit backstage waiting to walk on. It arrives at the cue. Not everyone was soothed. Einstein loved a world that goes on being itself, whether or not anyone looks objective, orderly, wrapped in locality and cause. To him, Copenhagen sounded like whispering. The moon disappears when you close your eyes. Bohr disagreed, but he did not answer with a grand metaphysical engine. He practiced a pragmatic humility. Quantum theory tells us what we can say about nature, not necessarily what nature is. Science, in this key is language polished for experiments, not a diary of the thing in itself. The complaint, then and now, is that Copenhagen prescribes more than it describes. It teaches you how to use the tools, how to evolve a wave function, and when to switch to probabilities of outcomes, but it refuses to replace the curtain with machinery. From that refusal grew a cultural shrug. Shut up and calculate. It is no line of bores, but it does capture the mood of many who build devices and compare data for a living. The theory works. It has not failed a test. Is that not enough? In practice, it often is. The Copenhagen rulebook underpins lasers, semiconductors, atomic clocks, the qubits we are learning to shepherd. Textbooks teach it, labs lean on it. Yet the unease persists like a draft through a window frame. If reality requires measurement to turn possibility into fact, what of the long eras before eyes and instruments? Was the early universe a fog holding its breath? Most physicists answer no. Observation does not mean a conscious witness. Any irreversible interaction that leaves a record, a detector click, a grain of photographic emulsion darkened, a whisper of heat in a sensor serves. The universe does not wait for minds, it waits for marks. But even that tidy distinction invites more questions. Which interactions count? Where, exactly, is the line where quantum evolution yields to classical outcome? Why should the world keep this odd rule at all? Copenhagen rarely offers a because, it offers a when. When a measurement is made, apply the postulate that assigns probabilities and selects an outcome. If you want an answer to why, you may need to walk further down the road. Many have. There is many worlds, which keeps the wave function smooth and unbroken, letting every outcome happen in separate branches rather than declaring a collapse. There is pilot wave theory, restoring definite particle positions guided by a deeper wave. There are objective collapse models, turning collapse into a physical process that happens spontaneously, especially in larger systems. Each tries to preserve classical comforts. Things exist with or without us. Cause leads to effect. The word measurement does not get special status. Each introduces its own price: multiplied universes, non-local guidance, new parameters, and noise. Against this bustle of alternatives, Copenhagen stays spare. No hidden variables, no branching cosmos, just evolve, measure, predict. Simplicity is part of its calm. In a field that already asks us to trade certainties for amplitudes, Copenhagen refuses extra scaffolding. It says, calculate the wave function as long as the system is closed. When an experiment extracts information, translate amplitudes into chances and settle on one result. The procedure is clear, and it has proven faithful. For many, that fidelity outweighs the hunger for an ontological tale. Still, the open ends tug. If reality clicks into a property when measured, what does that say about the moon before there were tides of thought? Most Copenhagen-leaning physicists reply that the universe has always been busy measuring itself. Particles scattering and leaving trails, photons entangling with dust, stars writing heat into space. Decoherence adds a crucial chapter to this story. It shows how contact with the environment washes out interference between alternatives and makes superpositions look like ordinary mixtures. Why cats in boxes don't sing interference fringes, why tables are stubbornly solid. Decoherence does not choose one outcome, but it explains why alternatives stop talking to each other so quickly that, for all practical purposes, a result is what we see. Bohr's language could be roundabout, almost lyrical. Those who are not shocked when they first come across quantum theory cannot possibly have understood it, he said, not to elevate confusion, but to legitimize it. The shock is a sign you have loosened your grip on old metaphors. Copenhagen does not claim to have tamed the mystery. It teaches a discipline. Speak only what experiments can decide. Treat the wave function as a tool for such speech. Except that some questions are misaimed. In that sense, it is less a philosophy than a posture, a way to work in the presence of uncertainty without demanding that uncertainty apologize. If that feels unsatisfying, it may help to regard the interpretation as a nightly ritual rather than a creed. You light a small lamp, you read the lines that tell you what tomorrow's measurements will reveal, and you put away the desire to name the machinery behind the curtain. The lamp is enough to cross the room. The curtain can wait. Copenhagen's endurance owes something to that quiet sufficiency. It does not forbid deeper stories. It simply declines to bet the lab on them. In a universe that often resists our categories, Bohr's rulebook reminds us to keep our language close to what can be written down in a logbook and checked by another pair of hands. Not a final answer, no, just a steady way to make correct predictions and to live scientifically with the strangeness intact. And if unease lingers, perhaps that is appropriate. The quantum world keeps some distance from our intuition. Copenhagen does not close the gap. It teaches us to walk it softly, carefully calculating as we go, letting the facts appear when asked, letting the rest remain a gentle blur beyond the edge of the lamp. Balance a coin on your thumb. You flick, it arcs through lamplight and lands with a quiet click. Heads. In the world you inhabit, that is the ending you witness. Yet one careful reading of quantum mechanics whispers a wider chorus of endings, each as real as breath. Somewhere, the toss yields tails. Somewhere, the coin quivers on its edge, rolls, and slips beneath the couch. Every outcome that could have unfolded does unfold. You wake in the thread that says heads. This picture carries a name, the many worlds interpretation. It keeps quantum theory's mathematics unbroken from start to finish. You know the wave function, the soft map of amplitude for what a system might show when asked. In the Copenhagen posture, it evolves smoothly until we measure, when a special rule says it collapses to one fact. In 1957, Hugh Everett III suggested dropping that rule. Let the wave function evolve by the same law always. Measurements do not destroy possibilities. They entangle system, apparatus, and observer. Everett's move is austere. Keep Schrödinger's equation everywhere. Stop adding a separate postulate for measurement. Think of an electron prepared so its spin may be up or down. Bring your detector near, and the combined system, electron, device, and observer, evolves into an entangled superposition of correlations. In one branch, the pointer reads up, and you record that fact. In another, equally concrete, the pointer reads down, and another, you records that fact. No outside randomness injected, no hidden hand collapsing anything. The mathematics is exactly the same as the standard calculation, only the extra command to pick one outcome has been retired. The price is conceptual abundance. The tree of reality gains a new twig each time alternatives become correlated and decohere. If that conjures shelves of cartoon universes, take a slow breath. Many worlds is not a hunt for sci-fi gateways. It is a lean statement about bookkeeping. Nothing magical happens the moment you look. The other branches are not neighboring rooms you could stroll into. Once entanglement has spilled which way information into the environment, decoherence prevents branches from interfering. They become for all practical purposes, causally isolated histories. Your instruments will never exchange messages across the divide, but the predictions you test in the lab remain exactly what quantum theory has always promised. Interference appears when amplitudes remain coherent. It vanishes when records leak into the world. The math you already trust keeps working. Many worlds simply declines to insert a special stop sign called collapse. A fair challenge follows. If the other histories can never speak to us, how could we know they exist? Supporters reply that many worlds asks you to assume less, not more. Collapse is an extra law stitched in at the moment our intuitions begin to itch. If every verified prediction of quantum mechanics follows from unitary evolution plus decoherence, why keep the stitch? Occam's razor cuts in two directions. Copenhagen conserves universes by spending an axiom. Many worlds conserves axioms by spending universes. Each kind of thrift feels honest to a different taste for simplicity. The question is not how to invent new phenomena, but how to avoid inventing them when the old machinery already accounts for what we see. Scale is where the pulse quickens. Branching is not reserved for dramatic measurements under bright lights. Molecules jostle in air. Photons scatter from dust. Nuclei decay on their own clock. With each quantum fork, the universal state unfurls new twigs. The branching is relentless, exponential, beyond easy imagining, yet unannounced. As you do not feel Earth's spin, you do not feel histories multiplying. You inhabit one thread, the rest hum beside you, unreachable and unthreatening, as quiet as other streets you did not walk this evening. And there is no travel, no messages slip between branches, no secret meeting with a self who ordered soup instead of salad. Entanglement builds the corridors, decoherence bricks them. That same architecture soothes a long-standing headache, defining measurement. There is no sacred threshold where quantum becomes classical. There is only the ordinary leaking of phase into the environment until interference cannot be restored by any practical means. Collapse becomes a nickname for this practical irreversibility, not a fundamental thunderclap. A calmer framework reveals a new riddle. If all outcomes occur, what is probability for? Why does it feel as though the coin landed heads, rather than that I fan out among head-seeing and tail-seeing successors? Many worlds invites a shift in grammar. Probability is not the cosmos picking one future. It is a measure of branch weight, the squared amplitude, that tells how much of your future's subjective measure flows into each result. Instead of asking, "What are the odds?" you ask, "What fraction of my future observers will register this reading?" The answer follows the familiar Born rule, not by decree, but by how rational agents should apportion expectations across branches they know they will inhabit. It is not intuitive on first hearing, but neither is quantum theory itself, and yet its numbers keep their promises. Because it keeps the mathematics tidy, Many Worlds has grown from a midnight thought into a working language. Its branching imagery pairs naturally with quantum computing, where algorithms choreograph interference among many computational paths at once. It also tempts those seeking quantum gravity, where space and time might emerge from patterns of entanglement. A universal wave function evolving without collapse provides a natural stage for such ideas. None of this proves the interpretation true, but it does show how a clean ontology can make new conversations possible without changing the equations that already succeed. Hesitation remains proper. If reality is a ceaselessly branching oak, does abundance slide into extravagance? Is accepting an uncountable multiplicity less modest than accepting one special rule. Reasonable minds differ. Copenhagen spares worlds by spending assumptions. Many worlds spares assumptions by spending worlds. Each economy claims a kind of simplicity, and simplicity, here, can point in more than one direction. Each path still tells a complete, local story, faithfully. Beyond argument, there is feeling. Some people find solace in a cosmos that discards nothing, that every path not taken is taken by kin you cannot meet. Others find the thought heavy, as though meaning thins when spread across so much reality. The interpretation itself offers neither comfort nor ache. It offers a grammar and a discipline. Treat measurement as entanglement. Treat branching as ubiquitous. Do the same calculations you would have done, then read either, or as both, kept apart. For tonight, try a quiet metaphor. Imagine a canopy rather than a maze. Each branch is complete. Each leaf drinks starlight. None steals from another. You owe nothing to leaves you cannot touch. They are not shadows of your life, but lives of their own. Parallel lines in a poem too wide to read at once. Your task remains local and human. Tend this leaf. Choose as though choices matter, because within your branch they do, without dilution or apology. Everett did not live to see how widely his seed would travel. For years, the idea felt like a rumor whispered after seminars, a provocation to be chuckled at and shelved. But as decoherence matured into a quantitative science, and experiments coaxed superpositions into larger and sturdier systems, the image of branching histories fenced off by environmental records became harder to dismiss. Even physicists, loyal to other interpretations, borrow its phrases when they describe open systems, pointer states, and the flow of information that turns coherence into ordinary facts. So hold the coin again, if only in memory. Feel the knurled edge on your thumb. When you flip, one story becomes yours. Elsewhere, the coin finishes differently. Ordinary, quiet, true. Many Worlds does not ask you to chase those endings. It invites a gentler thought. Reality may be a library, not a single book, a harmony, not a solo. Each branch keeps time with the same law. If the idea feels vast, remember, a library frames a page. Your page matters. Tonight you rest on one bright strand. Others glow beyond reach, to be acknowledged, not feared. Pull back the curtain on everything. The stars, the slate blue oceans, your chair, your hand, and the soft spill of light across your pillow, and imagine that none of it is built from tiny, hard beads. Imagine the most fundamental layer is not stuff at all, but vibration, invisible ripples, moving through fields that soak every corner of space. This is the gentle, radical picture of quantum field theory, where so-called particles are brief, bright crests on waves that never quite fall silent. Start simple. In classical physics, a field assigns a value to every point in space, the way a weather map paints temperatures or an electric field nudges a charge. Place a positive test charge in that invisible wind, and it drifts. The drift is the field speaking. Classical fields are smooth, continuous, and everywhere at once, a clear jelly the universe swims through. Quantum mechanics shifts the mood. It insists fields do not sit still, even when nothing obvious is happening. They flicker and hum because uncertainty ties energy to time. Perfect silence is forbidden. Even the vacuum, the state we once called nothing, refuses to be flat. It is restless, stippled with possibilities that rise and subside too quickly to watch, yet not so quick that they leave no trace. Now the leap. In quantum field theory, everything is a field. Every familiar particle, electron, photon, quark, neutrino, is a localized excitation, a ripple with a particular pattern of a corresponding field that fills all of space. An electron is not a marble with a shell. It is a quantized wave in the electron field, briefly gathered into a small place. The electromagnetic field ripples, and we name one packet of ripples a photon. Turn the ripple to a slower rhythm and you get radio. Lift it higher and you climb through microwaves, infrared, the colors of visible light, then ultraviolet, X-rays, and beyond. One field, many notes. There is a field for each species we know. Quark fields, gluon fields that bind quarks into protons and neutrons. The Higgs field, poured like slow syrup through the cosmos. If gravity can be made quantum, its smallest tremors, gravitons, would be ripples in a gravitational field as well. The old word particle does not vanish. It becomes a useful nickname for a packet-like ripple that travels cleanly and exchanges energy in discrete amounts. The field is the instrument. The particle is the plucked string heard as a note. This change of viewpoint replaces a universe of toy blocks with a symphony. Reality becomes interference and harmony between overlapping waves. Things are patterns that hold together for a while. Questions that felt awkward in simpler quantum stories find tender answers here. How can particles be created or destroyed in high-energy collisions? By shaking the right field. Pour energy into a region at a collider, say, and the field can be kicked into a new excitation. A particle appears because the instrument has been struck. How do antiparticles fit? They are counter-moving ripples in the same field, shaped by symmetry, mirror notes in the score. Forces themselves are field conversations. Charged particles exchange ripples of the electromagnetic field, photons, and we experience that exchange as attraction or repulsion. The strong force is the language of gluon fields, weaving quarks into hadrons. If gravity submits to quantization, space-time's gentle curvature would be carried by quanta of a gravitational field. Even when nothing counts as there, the fields remain, whispering in vacuum fluctuations that leave fingerprints. Two polished plates drawn together by the Casimir effect. Atom-scale energies shifted ever so slightly, spectral lines nudged into place. There is a quiet serenity in this view. Space is not a stage where actors stomp. It is an instrument already ringing, and matter is music. The instrument knows how to play. Every point is alive with potential. Every event, light, warmth, the click of a detector, is a story a field tells when it is nudged. The mathematics is not small. You do not sketch quantum field theory on a cafe napkin unless the napkin is the size of a blackboard and your chalk blossoms into Feynman diagrams, maps of how excitations can meet, split, and fuse. Yet the idea is tender and clear. Nature, at base, is not made of pellets. It is made of patterns, quantized and choreographed, energy arranged in space and time. Even mass, which feels like the most stubborn kind of thing, can emerge from how fields talk. The Higgs field resists certain motions, and that resistance shows up to us as mass. The more the field holds you, the heavier you appear. Inside protons and neutrons, most of the mass comes not from quark weights, but from the thrum of gluon fields and the kinetic dance of quarks themselves, a storm of energy bound into shape. Seen this way, you are a meeting of fields. The atoms in your breath are small, durable harmonies, played by electron, quark, and gluon fields. The signals racing along your nerves are rhythms in electromagnetic fields. Your thoughts are patterns, arrangements of excitations, sustained by chemistry and temperature and time. You do not end at your skin. The fields that define you fade outward, overlapping with the fields that define the room, the street, the trees, the night. There is no hard edge, only places where certain patterns are strong and others are faint. Quantum field theory also rescales nothing. The ground state of a field is not mute, it fluctuates, and those fluctuations subtly shift energies, nudge atomic levels, and bend forces. Include the vacuum in your calculations, and you match experiments better. The Lamb shift in hydrogen, delicate corrections to magnetic moments, the gentle push between plates. Remove those contributions, and the world drifts off-key. Yet this beautiful map has regions labeled mystery. If the vacuum seethes, how much energy does it store? Naively, the sum is catastrophically large, so large that, taken literally, the cosmos would rip apart. Observations say otherwise. Reconciling the calculated vacuum energy with the sleepy expansion we actually see is a profound riddle, a hint that our bookkeeping is incomplete or our subtraction clumsy. Even so, the field picture keeps paying its debts in accurate predictions and in technologies that lean on its truth. Semiconductors and lasers, magnetic resonance and particle detectors, qubits and superconducting circuits that coax coherent ripples to compute. Another grace of the field picture is how it softens borders. Creation and destruction are not births and burials of miniature marbles. They are the starting and stopping of particular patterns in a continuous medium. When two excitations meet, they do not slap like stones. They interfere, add, cancel, and when the math allows, become new excitations altogether. Conservation laws feel like harmonies. Energy, charge, spin, and momentum are symmetries. A field refuses to break, and each symmetry writes a rule the music must obey. Look around your room and let the edges blur. The lamp's glow is the electromagnetic field trembling in a visible key. The wood grain in your desk is quark and gluon fields frozen into a low-energy chord. Your heartbeat is chemistry keeping time with countless exchanged photons. You are not separate from this. You are composed of it, maintained, moment by moment, by fields that never turn off. Quantum field theory does more than describe the world. It retunes our sense of belonging in it. Reality is a weave, and we are threads localized, temporary, astonishingly coherent threads in a fabric that extends beyond any single touch. The fields do not end at the doorway. They continue through the dark and into the trees and out to the cold fires of distant stars. If everything is a ripple, one last question lingers, simple and endless. What is the ocean that carries all these waves? Tonight, let the question float like a small boat in a windless cove. Feel the room grow quiet. Hear the faint hum of the fields beneath your breath, soft, patient, and unhurried, guiding you gently into sleep. If the universe kept a tidy pantry, the standard model would be its labeled jars, everything we can cook with today, minus a few mystery spices we can smell but haven't yet found on the shelf. It's compact, a little whimsical in its naming, and astonishingly faithful to what experiments report back. Within this rulebook, live the ingredients and the rules for how they greet, bind, scatter, glow, and fade, the grammar of matter and the small forces that guide it. Begin with the players. At the deepest level we've reached, matter arrives in two families, quarks and leptons. Think of them as fundamental notes rather than composite chords. So far, we do not know how to split them further. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. The lightest 2 up and down do nearly all the visible work. 2 ups and a down make a proton. 2 downs and an up make a neutron. Stack those into nuclei, let electrons join the dance, and you have the fabric of tables, trees, sea spray, and breath. The heavier quarks charm, strange, top, bottom are rarer guests, summoned in high-energy flashes from accelerators and cosmic rays, brilliant and brief, yet essential to the full score. Leptons are the other half of matter's choir. The electron is the familiar voice, current in your lamp, bonds in your chemistry, the agile partner to protons in atoms. The muon and tau are heavier cousins, similar timbre, deeper register, short on patience. Each charged lepton travels with a neutral companion, a neutrino of matching flavor. Neutrinos are the quiet ones, rushing through planets and people almost without a handshake. Trillions cross you each second and seldom say a word. Line them all up and you find 3 neat generations. 6 quarks and 6 leptons, 12 matter notes set on the stave of quantum fields. Rules need messengers, and that's where bosons enter the carriers of the fundamental forces. Electromagnetism speaks in photons, quanta of light that have no rest mass, and therefore move at light speed. Photons bind electrons to nuclei, choreographing chemistry and color. The weak interaction, the one that lets neutrons transmute to protons and underwrites the fire in stars, travels by W mice, W menace, and Z bosons. They are hefty, which is why the weak force reaches only across the smallest distances. The strong interaction, which keeps quarks confined in protons and neutrons and tethers those nucleons inside atomic cores, is carried by gluons, 8 varieties of an always busy field that never seems to sit still. Gluons do not merely connect, they also carry the color charge themselves, weaving a self-knotted web whose tension gives most of ordinary matter its mass. And then there is the Higgs boson, confirmed in 2012, the brief crest of a field that pervades space like an invisible syrup. As particles pass through this field, some feel more drag than others. That resistance shows up to us as mass. Without this background, familiar particles would behave like weightless light, no atoms, no chemistry, no you. The Higgs does not bestow mass upon everything. Most of a proton's mass is strong force energy, but it sets the stage for quarks and leptons to be anything other than swift ghosts. Collect the cast, and you can recite the essentials: 12 matter particles, 6 quarks, 6 leptons, and 5 force carriers in this minimal recipe photon: W, Z, gluon, and Higgs. Gravity does not appear on this list. Its story is told elsewhere, by Einstein's smooth curvature of spacetime. Within its scope, though, the Standard Model is preternaturally accurate. It predicts scattering rates, decay widths, magnetic moments, spectral lines, numbers checked to many decimal places in colliders and cold labs alike. Over and over, experiments lift their eyes from the detectors and nod. Still, the model is not everything. It leaves out gravity's quantum face. It offers no particle that can make up the unseen mass tugging on galaxies, dark matter. It remains silent about the repulsive pressure accelerating cosmic expansion dark energy. In a cosmic census, only about 5% of the universe glows with Standard Model matter and light. But what of 5%? Stars and cells, mountains and music, the entire visible tapestry stitched from a modest alphabet that keeps spelling truths correctly. Spend a quiet moment with the structure. The model's symmetries, its internal handshakes and rotations are not decorations. They constrain who can talk to whom, which decays are allowed, and why charges come in the patterns we observe. Gauge symmetries give us the force fields. Spontaneous symmetry breaking gives us masses. Conservation laws fall out like steady drumbeats from the invariances nature refuses to abandon. Feynman diagrams, those spare little sketches, are not cartoons. They are compact sentences in the language of fields, tracking how excitations meet and part while keeping every symmetry promise. There is whimsy in the names strange, charm, top, bottom, but very little whimsy in the numbers. Couplings run with energy, the way river speed changes with slope. The strong force grows gentle at very high energies, asymptotic freedom, while at low energies its grip tightens until quarks never roam alone. Confinement. The weak force hides behind the mass of its carriers. Electromagnetism ranges far because its photon is massless. Each of these facts is a line in the same poem. Imperfections remain like soft creases in the page. Neutrinos, long assumed massless in the simplest version, do in fact possess tiny masses and oscillate between flavors, a clue the model has already been extended in practice. The matter-antimatter imbalance of the cosmos hints at further asymmetries we have not fully charted. The vacuum energy puzzle, why quantum fields' ground-state energy appears so small, cosmologically whispers that our subtraction scheme is missing a deeper story. And of course, the great marriage, still pending. A quantum portrait of gravity that sits peacefully beside this one without either demanding a divorce. Dreams of unity keep the chalk dust floating. Grand unified theories try to fold the strong and electro-weak forces into a single symmetry at high energies, promising that the separate threads we see now are strands of one thicker rope. Even bolder projects, string frameworks, loop quantization, emergent spacetime from entanglement seek a wider room where gravity and the standard model share a table. Perhaps the path is near, perhaps it bends through energies we will not reach for a long time. The impulse is the same one that built the model we have, the belief that patterns hide beneath complexity, that rhyme persists even when we cannot hear it yet. For now, the standard model is a completed chapter with dog-eared pages, inked in with precision and smudged where we keep turning back to reread. It does not describe most of the universe, but it does describe you exquisitely. The quarks laced by gluons in your bones, the electrons bound by photons in your breath, the weak interaction quietly at work in the sun that warms your skin, the Higgs field giving heft to the particles that make you more than light. If someone asks what the world is made of, you can answer softly. Mostly up and down quarks, some electrons and their shy neutrino cousins, with rarer kin, flashing into being when the energy is high enough. Forces speak through photons, gluons, and the heavy W and Z, while the Higgs field lends mass like a background tide. It is not the whole story, but it is a luminous beginning, an elegant list of ingredients and rules that, when stirred by time, compose everything from morning coffee to nebulae, and a reminder that even in a universe full of unanswered questions, so much can be known, and known well. Settle into the soft dark where numbers glow like embers, and meet a theory polished to a quiet shine. Quantum electrodynamics, QED, the gentle grammar by which light and matter exchange whispers. It explains every spark, glint, and electric sigh, and it does so with a poise that humbles decimals, predictions checked to parts per billion, as if a ruler lay across a continent and you read it within the thickness of a human hair. At its heart, QED tells the story of electrons and photons, their approaches and partings, the ripples they leave in one another. Accelerate a charge, and light unfurls. Bathe an electron in light, and its energy softly shifts. Physicists tried to calculate such meetings and found, to their dismay, that the math bloomed with infinity's answers as unhelpful as an ocean poured into a teacup. The puzzle needed honesty and a new kind of picture. Enter Richard Feynman, mischievous grin, quick hands, bongo drums standing alongside Julian Schwinger and Sine Itiro Tomonaga. Together they taught the equations to behave. Feynman's particular magic was to draw the conversation. In his diagrams, time drifts left to right. Straight lines mark electrons, wavy lines mark photons, and tiny vertices mark the moments they exchange a quantum of light. An electron may travel on, flick a photon into being, and continue. That photon may nudge a second electron or curl back as a brief loop. Each picture corresponds to a complex number, a probability, amplitude, and QED says, consider them all. Add every zig and zag, then square the magnitude of the sum, and the fog of possibility condenses into the likelihood of what you will observe. This is the path integral spirit, a sum over history so generous that an electron threads every route between A and B, around the hill, through the tunnel, beneath the bridge, and the universe weighs them all before offering one result. The miracle is that the arithmetic, though crowded with infinity's temptations, gives numbers that match the world. Renormalization, the careful redefinition of mass and charge, absorbs the dangerous divergences into a few measurable parameters. Fix those with experiments, and the rest of the predictions fall into crisp, finite alignment. Along the way, virtual particles make cameo after cameo. A photon can briefly split into an electron-positron pair and recombine. An electron can surround itself with a froth of momentary excitations. They cannot be netted directly, yet their influence is real. They screen charge at long distances and strengthen it at short ones. The running of the fine structure constant is QED's quiet admission that emptiness is active. Vacuum polarization and self-energy, once sources of nonsense, become tamed by the same renormalization recipe. The sums settle to values the laboratory can check. From that discipline flow triumphs. QED corrects the electron's magnetic moment, the tiny bar magnet strength that classical physics gets almost, but not quite, right. Quantum fluctuations nudge it by a whisper, and theory meets experiment to 10 or more decimal places. The Lamb shift hydrogen's spectral lines displaced by a sliver drops out naturally once the vacuum's jitter is included. Compton's scattering, where light ricochets from an electron, Bremsstrahlung, radiation from a charge that slows, and pair production, where a sufficiently energetic photon blossoms into an electron and a positron, all arise cleanly from the same rules and all agree with what detectors see. Part of the wonder is how small the rulebook feels. Feynman liked to say you could fit QED's core on a napkin, assign an amplitude to each possible path, multiply amplitudes for steps in sequence, add amplitudes for alternative routes, square the absolute value of the total to get a probability. Conservation laws keep time, Phases keep harmony, and the rest is careful bookkeeping. The diagrams are not cartoons, but compact calculus maps of how fields exchange quanta while keeping symmetries exact and the balances of energy, momentum, and charge intact. QED also set a template. Electromagnetism's quantum field is abelian and gentle. Weave the same ideas into a non-abelian cloth, and you get the strong interactions quantum chromodynamics, where gluons carry their own charge and tangle like vines. Join electromagnetism to the weak force, and electroweak theory emerges, hiding symmetry behind the Higgs field's quiet pressure, so W and Z bosons grow heavy while the photon remains light. In every case, Feynman's language persists. What changes is the alphabet of charges, couplings, and self-interactions. Precision, however, has its borders. QED, magnificent as it is, does not include gravity, and it does not explain dark matter's patient pull. Within its domain, though, it stands unsurpassed, the most stringently tested framework we own. Even Feynman, wary of pedestals, admitted the theory's extraordinariness, then reminded us not to grow proud. Nature, he liked to say, keeps more cards than we know. Perhaps that is the loveliness here. QED captures an endless shimmer without requiring the mystery to disappear. It lets you compute the glow of a bedside lamp, the blue of the sky, the timing of a detector's click, quiet, practical things, and it does so with a confidence born of many careful comparisons with reality. When you swipe your screen and see it wake, photons leap and land by these same rules. When you look up at winter stars, their ancient light has scattered and shifted and survived by the same arithmetic. Even the dim green of auroras and the crisp bite of laser light are QED at work, sturdy and exact beneath the beauty. So lie back and picture the sums like threads pulled through fabric. Every interaction is a tapestry woven from possibilities. Every loop a rehearsal for events that cannot stand alone yet steer the whole. The diagrams on paper are lullabies for grown minds, lines that meet, split, and rejoin, phases whispering yes or no. Behind them rests a principle so simple it almost sounds like a bedtime story. The world explores every way it can. What happens is the chorus of those ways, sung in complex numbers until probabilities appear. QED may not be the last word, but it is a clear one, an art of prediction whose decimals seem content, a dance of electrons and photons stepping lightly over the unseen. If future physics writes a deeper score, it will keep this melody. For now, in every spark and screen glow, in each quiet reflection on the window pane, the theory hums along exact and unhurried, gathering all the paths and, at the end, offering the single flicker you see. Imagine a careful librarian and a night-soft poet sharing the same desk. The librarian turns pages in order, quick, tidy, reliable. The poet hums overlapping lines, tasting several pages at once, then chooses a single verse to keep. Classical computers are the librarians, disciplined, deterministic, astonishing at step-by-step work. Quantum computers lean toward the poets. They let many possibilities murmur together, then shape those whispers, so one answer rises. It sounds like magic. It isn't. It's the quiet logic of the quantum world, harnessed with patience and cold, careful hands. To see why they're different, meet the qubit, the bit's peculiar cousin. A classical bit is either 0 or 1, like a switch snapped off or on. A qubit rests in superposition, awaited both. that hold 0 and 1 inch the same breadth until you ask. Picture a coin spinning on velvet, not heads, not tails, a poised becoming. 1 qubit already carries more possibility than a bit. With 2 qubits, you can choreograph 4 patterns at once. With 3, 8. With n, a vast space of 2 Wu amplitudes, complex numbers that describe how strongly each pattern is present. The power creeps in exponentially, like a choir whose voices double and double again. But superposition is only half the spell. Entanglement links qubits so that learning about one tells you something certain about the other, even if they sit far apart. It's not a faster-than-light message. It's a correlation woven during preparation, a choreography that lets operations ripple through the register in ways no classical memory can imitate. Entangled states are richly structured canvases, and quantum algorithms paint on them with interference, brightening some outcomes, dimming others, sculpting probability itself. That sculpting is the heart of quantum parallelism. A classical program explores paths in sequence or in carefully scheduled parallel threads. A quantum program spreads amplitude across many computational paths at once, then interferes them, so wrong answers cancel while right answers reinforce. You don't harvest every possibility. You shape the landscape so that when you finally look, the correct result is more likely to appear. It's like carving a shallow valley so a marble rolls to the right spot and rests. When you can nudge probability, certain problems bend. Simulating molecules is the flagship example. Electrons are quantum creatures, and their shared wave function blooms beyond classical memory. Quantum algorithms speak the system's native tongue, promising better routes to reaction energies, catalysts, superconductors, and battery materials. In optimization delivery routes, timetables, resource allocation quantum routines may tilt the landscape efficiently, guiding searches through thorny spaces. And for factoring large integers, Shor's algorithm offers an exponential advantage in principle, which is why today's cryptography is already planning its next shelter. Now for the hush behind the glamour. Qubits are delicate, stray heat, tiny vibrations, a whisper of magnetic field, a lone microwave photon. Each can scramble phase and unravel entanglement. Many devices must live near absolute zero, colder than deep space, so random motion quiets. Even then, errors creep in. Bit flips, phase flips, leakage into levels you didn't ask for. Unlike classical data, quantum states cannot be freely copied for backup. The no-cloning theorem draws a firm line. So engineers weave protection another way: quantum error correction. They spread one logical qubit across many physical ones, detect the subtle footprints of noise without measuring the information itself, and gently steer the state back. It's like wrapping a candle's flame in glass and still letting it breathe. Because so much effort goes to protection, today's machines are called NISQ, noisy, intermediate-scale quantum. They carry tens to hundreds of qubits with finite coherence. Some teams have reported quantum advantage, finishing narrow tasks that would choke classical supercomputers. Others explore near-term chemistry, materials, sensing, and optimization, where noise can be tolerated or cleverly canceled. Progress feels tidal, not a single wave that crowns the shore, but many small swells that keep arriving. The logic gates are different too. Instead of and or, we use rotations and entangling gates like C-knots to sculpt amplitudes. Measurement ends the dance. translating complex numbers into an ordinary string of bits. Run the circuit many times, gather a distribution, read its shape. Under the hardware lies familiar music, unitary evolution, interference, and the Born rule, which turns amplitude into chance. Hardware comes in several dialects. Superconducting qubits are etched on chips and steered with microwave pulses. They're fast and tile neatly into two-dimensional arrays. Trapped ions float in electromagnetic fields. Lasers write gates with exquisite fidelity over long coherence times. Neutral atoms sit in optical tweezers. Rydberg interactions draw programmable graphs of entanglement. Spins in diamond and photons in waveguides offer other paths, each trading speed, noise, connectivity, and footprint in a different balance. No single approach has won. Each teaches the others how to be quieter, steadier, kinder to coherence. Security is changing as well. A future fault-tolerant quantum computer could break widely used public key schemes by factoring large numbers efficiently. In response, standards bodies are adopting post-quantum cryptography, classical algorithms believed to resist quantum attacks. The migration will take years, which is precisely why it has begun now. Keys chosen today may need to hold fast for decades. Will quantum machines replace laptops? No. Classical computers remain unmatched for everyday work and for vast provinces of science. Quantum processors are special-purpose instruments, valuable when their native physics matches the problem's structure. Think of them not as replacements, but as new senses, a way to feel landscapes that used to be numb under our feet. The future looks collaborative, classical and quantum tools sharing the same bench, handing sub-problems back and forth like careful friends. Perhaps the loveliest twist is how the once weird becomes useful. Superposition stops being a riddle and becomes a resource. Entanglement, once spooky, becomes wiring. Even measurement, the collapse that picks a single outcome, becomes a step in the algorithm, the moment probability cashes out as an answer. Every decohered qubit is a lesson. Information is physical and fragile, and worth protecting like flame in wind. Where does the path lead? Toward fault-tolerant machines that run deep circuits without forgetting. Toward quantum networks that distribute entanglement between distant labs. Toward sensors that sip at nature's limits, gravitational, magnetic, inertial with astonishing grace. The timelines are honest and long. Yet already, the work is changing how we think about computation. Not a single thread through a maze, but a careful braiding of ghostly paths that settle at the last moment into something you can hold. Call classical computers librarians and quantum computers poets if you like. The future is a duet. The catalog and the chorus together will map problems we couldn't reach alone. And if the metaphor helps you drift, imagine an algorithm as a dark river seeded with countless ripples. Imagine measurement as the shore. You extend your hands, the ripples fold together, and one cool shape remains. That is the answer. Soft, precise, and real. That is quantum computing's quiet promise, steering possibility tenderly until a single line of truth comes to rest in your palm. We expect the small to be strange, down where matter blurs, particles slip through walls, spin two ways at once, and keep secrets with partners across impossible distances. What we don't expect is for that strangeness to keep its shape in places that feel so human, warm and wet, humming with chemical bustle. Biology is noisy. Quantum effects are shy. We refrigerate qubits to near nothing, and coddle them from the slightest tremor. Life, meanwhile, goes on at body temperature, splashed with water and light. And yet, in feather and leaf and breath, quiet hints keep appearing. Nature may be using the same delicate rules we whisper about in labs, and using them well. Consider the robin's small, alert, a heartbeat of color on a branch, and its astonishing certainty about north. Migratory birds find their way through fog and night, over country and sea, as if the planet itself were softly tugging a thread inside their bodies. The old guess was right. Something like a compass must be there. The surprising part is how it might work. Inside the eye, tucked into a light-sensing protein called cryptochrome, a photon can set off a reaction that briefly creates a radical pair. Two electrons born together, whose spins start out entangled. Earth's weak magnetic field is not strong enough to yank iron needles, but it is strong enough to tilt the quantum phase of those spins. The chemistry that follows depends on that tilt. Change the bird's orientation, and the relative probabilities of product pathways shift. The result is not a little arrow, but a pattern, perhaps a dim blue map superimposed on vision telling the robin which direction is kind. This sounds too fragile to survive a blink, let alone a flight. Entanglement usually evaporates when the world breathes on it. But in carefully designed experiments, light-activated molecules show spin-dependent reactions that respond to magnetic fields as faint as Earth's. Behavioral studies find birds lose their way under certain magnetic noise. The puzzle is not solved. It is, however, less improbable than it once seemed. If birds truly feel direction through the choreography of entangled electrons, then evolution has learned to cradle coherence in a bright, wet cell, an engineering trick we are still learning to sustain. Now walk from feather to leaf. Photosynthesis begins with a small miracle repeated all day. A photon lands, and a plant stores its energy with astonishing efficiency. The plain picture says energy hops from one chlorophyll to the next randomly, like a visitor knocking down corridors until, happily, the reaction center opens its door. But measurements hint at something more graceful. In certain light harvesting complexes, the excitation behaves like a wave train, an exciton that spreads over several pigments at once. For a fleeting moment, picoseconds, which in this realm is long enough to matter the system, preserves a whisper of phase, letting different roots interfere. The energy doesn't merely try paths, it compares them, canceling the long way around and brightening the short. The maze is no longer walked, but felt, and the quickest route glows. Warmth should scramble those phases. And indeed, coherence in these complexes is brief, but brief is not the same as useless. A few picoseconds is all the time a molecular machine needs to nudge probability in the right direction before the environment takes over. In some organisms, special architectures, careful spacings, couplings, and motions may help keep coherence long enough to tip the odds. Does every leaf on every branch rely on quantum interference? Not necessarily, yet the repeated suggestion is clear. Evolution can build scaffolds where even soft, short-lived coherence becomes a tool. There is another sense where quantum rumors linger: smell. The simplest story is shape. A molecule fits a receptor, as a key fits a lock. The lock signals. You experience jasmine or smoke. But shape alone struggles to explain certain mismatches. Similarly shaped molecules that smell unlike, and very differently shaped ones that rhyme. An alternative, the vibrational theory, adds a line to the score. Receptors may be sensitive not only to fit, but to the frequencies a molecule's bonds can hum. In this view, when a molecule binds, an electron may tunnel from one part of the receptor to another through the bound molecule. Whether that tunneling is allowed depends on the molecule's vibrational energy gaps, on whether the electron can give up exactly the right amount of energy into the molecule's tiny springs. Change a bond to its heavier isotope, and the frequencies shift. Intriguingly, in some studies, humans and fruit flies can tell such twins apart by scent. The evidence is mixed, controversy's real, but the possibility is lovely. Your nose, as both sculptor and musician, using shape and vibration, structure and quantum tunneling to parse the world. Step back, and a theme appears. In each case, avian navigation, harvest of light, hints in olfaction. The quantum ingredient is not the whole meal. It is a seasoning that, added at the right moment and place, tilts outcomes in a favorable direction. Life does not need coherence for hours. It needs it for a breath's worth of molecular time. It does not need undying entanglement. It needs a fleeting link, strong enough to bias chemistry before warm water jostles the pieces apart. Evolution is patient. Give it billions of years and it will test every hallway in the house, keeping those that guide energy more efficiently or sense the environment more finely. There is humility in this. The mathematics we use to describe electrons in vacuum tubes turns out to be the same mathematics that may help a robin read the sky. The interference patterns we peer at in darkened labs echo, perhaps, in the way a leaf is kind with light. Even the tunneling we carefully coax in semiconductors might flicker in your nose as you catch the first hint of rain on pavement. Physics does not build fences between domains. It lays one grammar under many stories, and biology, messy, wet, alive, learns to speak that grammar with a local accent. Quantum biology is young. Many of its boldest claims will be refined, some refused, others strengthened as measurements sharpen. That is how science breathes. What remains, even as details shift, is the sense that the small is not quarantined from the living. The same rules that guide electrons along gold wires and photons through fiber also whisper in chloroplasts and cryptochromes, in receptors and enzymes, in the slight, precise steps of molecular dances that keep us fed and oriented and aware. If we can learn from these natural tricks, we may build better sensors, smarter solar cells, gentler chemistries. More important, we may feel a little more at home in the universe. The strangeness we meet in textbooks is not some distant oddity. It threads our mornings and evenings, the way birds depart and return, the way leaves turn light into sugar, the way a memory of cinnamon wakes a room. Life has been playing with the strangest tools in the box for a very long time. We're only now, quietly, beginning to notice the music. At the tiniest scales, matter behaves like a poem, whispered in overlapping lines. Electrons spread as possibilities, interfere with themselves, and hold several futures in the same soft breath. Yet the room around you is not a rumor of maybes. It is a steady scene, a warm mug, a quiet desk, a cat whose state is mercifully singular. How does a world woven from probabilistic threads feel so firm beneath your hand? The answer is a quiet process with a gentle name: decoherence. It is how quantum music, so easily smeared by a touch of air or light, fades into the harmonies we call classical. Decoherence does not thunder, does not announce a sudden collapse. It works like dawn-lifting mist, slow enough to watch if you could see that small, fast realm until the fog of alternatives thins and one outline stays. Begin with a lonely quantum say, an electron prepared in a superposition of here and there, left perfectly alone, sealed away from every stray photon and passing whisper of field. It keeps its delicate phase relationships. The two possibilities can still meet and interfere, like ripples crossing on a still pond. But perfect solitude is rare. On Earth, warmth presses in. Light strays, molecules drift and bump. The electron state becomes entangled with these countless surroundings, and with each tiny encounter, information about here versus there leaks out into the world. That leak is the essence of decoherence. The superposition is not destroyed, it is shared. Phase is the relative timing that lets alternatives interfere, spread into a million environmental degrees of freedom. From your point of view, those phases are gone. You cannot gather them back. The interference terms that once mattered blur to almost nothing, and the system begins to behave as though it had chosen a single track. As though is important. Nothing in the fundamental equations demands a jump. Rather, the usable quantumness has been diluted into everything else. Think of privacy. A quantum state is most itself when no one is listening. The moment the environment eavesdrops through collisions, scattered light, or soft vibrations, the secret is out. Not because a person looked, not because a conscious mind intervened, but because nature is always exchanging tiny messages. Each message is a trace in the air, a photon that ricocheted, a phonon that carried away a hint of where the particle leaned. After enough traces spread, there is no way, in practice, to make the alternatives touch again. The handwriting of interference is smudged beyond repair. For small things, carefully sheltered single atoms in traps, ions suspended in electric fields, superconducting loops cooled toward absolute zero, coherence can linger long enough to show its signature fringes. But as systems grow complicated, many particles, many ways to couple to the world, the decoherence time shortens to a breathless instant. A dust mote, bathed in sunlight, loses phase coherence in far less than a trillionth of a second. A shoe, a sandwich, a coffee cup, their quantum options have already been handed to the room by the time you finish the thought. That is why you do not open a refrigerator and find a lunch smeared across positions like watercolor. The watercolor has dried, the phase has fled. In this sense, decoherence hides superpositions rather than bans them. Deep down, everything is still described by a wave function that, in principle, holds all the alternatives. But those alternatives are entangled with so many untracked details, air currents, scattered light, the soft thermal shiver of the world, that they cannot interfere in any way you could observe. The quantum possibilities still exist within the all-inclusive description, yet they are locked away behind a haze of lost information. Classical certainty is what remains after the interference has been whisked out to sea. This perspective also softens the long-standing puzzle of measurement. Decoherence alone does not name the outcome. It does not tell you whether a detector will flash left or right, but it explains why, for everyday objects, you never see the telltale marks of quantum superposition. The cat, in its box, is entangled with the molecules of the air. The texture of the box, the radiation of the room, almost immediately. Even before you lift the lid, the distinct stories alive, not alive, have become unable to talk to each other. To you, that feels like a collapse. In truth, it is a loss of coherence, so thorough that the alternatives can no longer interfere and so appear, for all practical purposes, as separate classical outcomes. A different picture might help. Imagine writing with invisible ink that glows only when the room is dark. In perfect darkness, letters from two different sentences can overlap, and their patterns interfere an elegant, private script. Turn on the light, let the environment flood in, and the glow is drowned. The ink is still there, but the interference is gone. You now read one ordinary sentence. Decoherence is that light, not judgmental, not abrupt, simply overwhelming. For technology built from quantum fragility, decoherence is the ever-present breeze that threatens a candle's flame. Quantum computers must keep qubits coherent long enough to choreograph interference on purpose. Every stray photon, every mechanical tremor, every thermal wiggle can scramble the delicate phases that make the computation work. That is why such machines live wrapped in metal cans and dilution refrigerators, why error-correcting codes spread one logical qubit across many physical ones, sensing and nudging away noise without peeking at the secret itself. In sensors, two magnetometers, interferometers, clocks. The art is to tend coherence just long enough to let the world imprint its faint signal before the wind of decoherence carries it off. Decoherence also sheds light on why certain states are the ones we ever see. Some configurations, so-called pointer states, are unusually robust under environmental gossip. Position, for instance, gets recorded everywhere. Photons scatter from where an object sits. Air currents feel its presence. Surfaces carry its slight warmth. Momentum, or delicate superpositions of positions, have fewer natural guardians. The environment, without consultation, selects the stable states by constantly monitoring them. It is not an act of will, merely a habit of physics in a busy room. None of this claims to settle every interpretive question, whether the wave function is a real physical field or a ledger of expectations, whether only one outcome exists or many branch. Why this outcome arrived here? Those are open doors where patience and experiment still walk. Decoherence does something simpler and essential. It builds a sturdy bridge. On one side is the universal quantum evolution, unitary, reversible, happy to entertain superpositions. On the other side are the regularities of daily life, chairs that stay where you put them, keys that do not smear across the hallway. The bridge is not a gate. It is a long ramp, and as systems roll down it, interference effects leak away into the world until only classical tracks remain. If you want one more image, try this. A chorus begins perfectly in phase. Voices rise and fall together, building clear, bright interference. As the hall fills with echoes and footfalls, each voice picks up a slightly different delay. The choir is still singing, but the clean patterns blur into a warm wash of sound. Decoherence is that wash. The music does not end. It becomes something you cannot parse into the fine combs of constructive and destructive interference. What remains is harmony broad enough to feel like certainty. So when your hand closes around a mug, and it is exactly where you expect, thank the world's constant conversation. Thank the air for carrying away the delicate clues that would have let the mug be elsewhere in the same breath. Thank the light, the warmth, the soft seismic murmur of the earth, all the little witnesses whose relentless listening makes large objects behave. Beneath the surface, the water is still moving. Decoherence is the skin of ice, thin for the small and sheltered, thick and trustworthy for the everyday. It keeps us from falling in, even as the lake hums beneath, a quantum restlessness shaping the stable patterns we call real. Imagine a hallway of moonlight with a curtain in the middle. Behind the curtain are two doorways. You send one soft pulse of light toward the curtain and decide, only after the pulse has already passed, whether you'll peek to see which doorway it used, or keep your eyes gentle and let the wavy mystery be. Somehow, the pattern you later find on the wall seems to respect the choice you made late, as if the past waited for you to make up your mind. It's here, in these twilight games, the delayed choice and the quantum eraser, that time itself feels loose, like a ribbon the universe ties in unexpected knots. Start from the familiar strangeness, the double slit. When you don't ask, which slit? The arrivals on the screen bloom into an interference pattern. Bright, dark, bright like ripples overlapping on a pond. Ask the which path question with a detector, and the ripples vanish. The screen fills with the plain distribution you'd expect from little pellets. The knowledge matters. The very availability of which path information changes what the world is willing to show. Wheeler's delayed choice leans into that dependence and adds a mischievous twist in time. Build your apparatus so that after the light has already encountered the slits, or a beam splitter in a Mach-Zehnder version, you can still decide, do I set things so the paths interfere? Or do I arrange the detectors to reveal a trail? Make the decision late, so late it feels you are choosing after the fact. Then look. When your setup preserves the possibility of interference, you find wave-like results. When your setup would reveal the path, you find particle-like results. It's tempting to say the photon knew what you would do and behaved accordingly in the past. The gentler truth is that quantum events do not become a story with definite chapters until the whole experiment, beginning to end, is considered as one scene. The outcome is written by the configuration as a whole, not by a single moment taken in isolation. And then there is the quantum eraser, which sounds like a magic trick, but behaves like careful bookkeeping. The idea is to mark the paths so that, in principle, you could tell which slit each particle used, perhaps by entangling it with a partner that carries a path tag. Once that marking exists, interference goes mute. But if later you erase the which path mark, choose a measurement on the partner that makes the path information inaccessible, the interference can be recovered. Not on the raw pile of hits, those remain bland, but in the sifted subgroups you make afterward, sorting events by how the partner was measured. In those conditioned patterns, fringes and anti-fringes reappear like ghost lace, revealing that coherence was not truly destroyed. It was hidden in correlations and then brought back into view. This is the part that makes clocks feel soft. You can erase the which path clue after the first particle has already been detected, and the fringes slide back into the properly paired data as if the past had been persuaded. But no message travels backwards. No decision you make can rewrite a record or send a signal to your earlier self. All that changes is the story you can read when you gather the full tapestry of outcomes and look at the right threads together. Quantum mechanics is not revising history. It is refusing to assign a single history until the questions are fully posed. One way to rest with this is to think in terms of information. In the small world, the availability of which path knowledge, whether anyone actually looks or not, spoils interference. When the information could, even in principle, be known, the wave patterns go quiet. When that information is forever out of reach, erased, scrambled, or never written, the possibility of interference returns. The grammar of the quantum is less about little objects moving along tiny tracks, and more about how different alternatives keep their phase relationship or lose it, depending on how the entire experimental conversation is staged. Another way is to picture a garden of paths under moonlight. If the exits are arranged so the paths fold back together without leaving any footprints, the ripples from every route can meet and sing. If the paths are marked even faintly, the footprints carry phase away into the environment, and the choir falls out of alignment. Later, you can decide to ignore those footprints by measuring in a basis that washes them out, and the harmony returns in the subgroup where the footprints cancel one another. The song did not vanish. It was entangled with too many small echoes to hear until you chose the ear that could listen. Interpretations offer different lullabies. Some physicists speak of entanglement and correlation without invoking causes that run backward. The statistics are shaped by global constraints, not by signals darting through time. Others find comfort in the block universe, where past and future coexist like frames on a film strip. Your late choice is simply another part of a timeless whole. Pragmatists smile and say the calculation is clear. Set the apparatus thus, get fringes. Set it so, get none. All agree on the essentials. No paradox can be used to send a message to yesterday, and macroscopic causality does not break. The weirdness lives in how the quantum world withholds a crisp narrative until you ask a complete question. If that still feels slippery, let the metaphors slow your breathing. Imagine writing a story in pencil across transparent pages, then stacking the pages. On one page, the character turns left. On another, right. If you look at a single page, the path is clear. If you press the stack together in the right alignment, the translucent lines overlap into an interference pattern, a moire of possibilities. Now, very late, you can choose to slide the pages into a position that makes the moire visible, or offset them so only the crisp, single path remains. You did not alter any page. You chose how to read the stack. The lesson is not that time misbehaves for fun, but that our everyday sense of before and after is built for coffee cups and doorways, not for delicate superpositions. Down where outcomes are amplitudes first and facts second, the world asks for whole experiment questions and answers that respect the entire arrangement. The delayed choice and eraser experiments do not shatter physics, they illuminate it. They show that reality, in its quantum phase, is hospitable to many intertwined drafts. What becomes the draft you hold depends on which questions you finally put to the paper and how completely you gather the pages when you look. So if midnight ever makes you wonder whether the past is as settled as it seems, take comfort and wonder both. The universe is kind to large things. Causality holds your days together. Beneath that kindness, in the small hours of the small world, possibilities braid through time until a full question is asked. Ask it one way, and you receive waves. Ask it another, and you receive paths. Either way, the answer arrives like a calm exhale, and the river of moments flows on. Quantum physics says reality at its core is probabilistic. Individual outcomes are genuinely random, yet their statistics are exquisitely ordered, yielding the reliable classical world we experience. This built-in randomness isn't a flaw. It seeds novelty, complexity, even life, while ensembles of countless events average into stable laws. It also reframes reality itself. Before measurement, systems live as layered possibilities, and observation helps select a single story. Rather than promising certainty, quantum theory offers humility and wonder. an invitation to see uncertainty as a feature, and reminds us we are participants in a cosmos still unfolding with possibility. So, here at the edge of night, after drifting from glowing coals to flickering photons, from wave-slashed slits to whispering entanglement, from tunneling sparks to restless fields, from QED's fine decimals to qubits' soft chorus, from robins and leaves to the hush of decoherence and time's playful knots, let the questions loosen their laces. The universe does not promise certainty. It offers patterns and possibility, laws that hold like constellations, while single stars still shimmer. Reality, it seems, is both music and instrument, both map and wandering, choosing one note whenever we listen, keeping 1,000 more humming just out of sight. So let the lights fade to a friendly gray. Let the window glass cool beneath your palm. Above, the long seam of the Milky Way is coasting east. Below, your breath finds an easy tide. If the world is woven from maybes, then rest inside them weightless, welcomed knowing that bridges and atoms and heartbeats remain faithful while the small things dream. Close your eyes. Let moonlight unspool into darkness. Let thoughts thin like mist over water, and follow that quiet current where answers are not required, only wonder. When morning returns, the laws will still be waiting. For now, float unhurried, unafraid into the soft, star-slow drift where the cosmos keeps time and you become gently part of its sleep.